Are there questions? Yes. Okay.
One is when you're putting the, let's say if you're putting a Ramon condition on left sector, then we need to put same condition on all Fermionic things, right? We can't pick a few, right? Because the Lorentz.
Yeah.
And the second question I have is this: if you start off with, let's say, particular one sector, NS sector, let's say, and try to construct a string theory, just a spectrum out of it.
Yeah.
You at some point said that this will not be consistent string theory. You need to consider other also, right?
Yeah.
You can't separately take one sector and construct out.
That's it. Yeah. Yeah. So I'll discuss the reason behind it maybe a little later. So basically, what happens is that you cannot. So if you just include NS sector, right? Then at tree level it is consistent. That when you collide two NS particles, you find that it has NS sector only. But at one loop, it's not consistent, right? It loses modular invariance.
I think the other sector will start appearing.
Yeah, that unless you put the other sector in the loop, you find that it's not consistent with the Walsh diffeomorphism.
All four for that.
You need all four. Yeah. Right. If you just use Ramon sector, right, then Ramon sector is not even consistent at tree level. Because if Ramon sectors are fermions, so if you collide two of them, right, it will produce a boson.
But if someone is not interested, okay, that's just boson. If someone is only interested in, let's say, Fermionic theory, then you can't really construct, right? Because boson theory you can construct, but just Fermionic.
Yeah, okay, you can construct if the collision of two fermions don't produce a boson, right? But that will not be the case here. If you collide two fermions, you find that you produce a boson, and if you don't include that contribution in the final state, you lose unitarity, right? Because you are throwing away some states by hand. Any other question? Okay. So let me recall where we had ended. Yeah.
If we start compactifying certain directions, then we anyway don't care about those directions having Lorentz and Dirichlet.
That's true, yeah.
So we can then independently fix the Ramon-Navier-Stokes in the compact directions.
Yeah, well, you can try to do many things, but you have to make sure that things are consistent, right? And you will find that it's not consistent because, for example, the worldsheet supersymmetry, right? It relates x mu to psi mu, right? And worldsheet supersymmetry, there's only one parameter, right? So if you use independent boundary condition on the psi mu's, right, then the worldsheet supersymmetry is no longer a symmetry, right? So what you saw is that worldsheet supersymmetry, if you go through the Ramon sector, you have to take epsilon to be antiperiodic, right? Or epsilon to be periodic along the circle. Okay? In the Navier-Stokes sector, epsilon is antiperiodic, right? Because x is always periodic, right? And psi is periodic in the Ramon sector and antiperiodic in the Navier-Stokes sector, right? So the epsilon has to be similarly periodic or antiperiodic. But if you try to use different boundary conditions on the different size, right, then there is no epsilon will do the job, right?
Are you in a situation where you can relax the worldsheet to get the space and supersymmetry?
The point is, in this case, the worldsheet supersymmetry is inherited from a gauge symmetry, right? Worldsheet, local worldsheet supersymmetry, and that you cannot break. Okay, so you can ask if in a purely bosonic string theory you can get fermions, right? So far, nobody has found a way to get fermions out of in purely bosonic string theory because you need this Clifford algebra, right? To get fermions, you need spinor representation, right? So for that, you need some Clifford algebra. That happened here because of fermion zero modes form the Clifford algebra. If you only have bosonic worldsheet, right, then there is no, there's no Clifford algebra, right, underlying it. Any other question?
Supersymmetry was not a requirement from that point of view.
Worldsheet supersymmetry was a requirement.
There is some number of spinors. Why not? I didn't get the point.
No, the states have to be, you cannot include anything that you like in string theory, right? The states have to be formed out of the CFT, right? So the way you started, suppose you start with only the x mu, right? And some internal degrees of freedom. Then you cannot get Clifford algebra of the SOD minus 1, right? How will you get spinor representation? Out of X mu's, you cannot construct spinor representation, right? Products of X mu's will not do the job.
Yeah,
Right?
okay.
Similar products of psi mu's also don't do the job, right? But for psi mu's, there is a special case when you have a zero mode of the psi mu, right, which form a Clifford algebra, and then the representation of those zero modes is a spinor representation.
Means these
Not the B, yeah, B mu zero, exactly. Yeah, B zero mu. Right? The spinor representation came from there, right? Because B zero mu's formed a Clifford algebra, right? So that shows that you cannot take all the B zero mu's to annihilate the state, right? You can take half of the B zero mu's to annihilate the state. You choose arbitrarily, and then the other half are like creation operators, and they create a spinor representation. Is this okay? Any other question? Okay, so let me begin by recalling what the spectrum was. So the spectrum contains 4 sectors, NS. So let me start with NS. So here the spectrum contains the ground state K. Okay, for a given momentum, it's a unique ground state. Okay. And then we apply products alpha mu n, alpha mu minus n, for I don't know what I call them, R, P and Q, P mu n, or Q or R maybe. Okay. Here the U mu n and V mu n can take value 0 or 1. Okay, because squares of these operators are 0. Okay, from the anti-commutation relation. These can take arbitrary values, Q and R. And N, let me write this as R. N is integer and R is integer plus half. Okay, this is in the NS sector. In the NSR sector, we can write a similar thing. Here A and A dot refer to the 2 spinor indices, right? Because so in we had already said that the theory is consistent in D equal to 10, okay, which we have not proven, but we will see it later. Okay, so SO 9, 1 has 2 inequivalent spinor representations, which are chiral and antichiral. So A and A dot refers to chiral and antichiral spinors. Yeah, so we choose both of them, right? But the rules are different for the 2. Okay. So first of all, R belongs to, I should use a different symbol here, R prime. Here R belongs to Z, R prime belongs to Z plus half. Okay, because this is Ramon sector, this is NS sector. So right is holomorphic, right is B. Right? Yeah, you have to fix the convention once and for all. Right? Right is holomorphic, right? So B refers to right. But it's up to you to choose. If you like the other one, you can translate it. Okay. So R belongs to Z, R prime belongs to Z plus half. N is always integer, right? So I'm not even writing it. Okay. And then these are again 0 or 1. Okay, again I'm not writing it because that's the same. Okay. But now the GSO projection tells us that sum over, I should have said the GSO projection. Here the GSO projection is the sum over U mu R is odd, sum over V mu R is odd. Because we declare the ground state to be GSO odd, okay, under both left and right sector. So to get a GSO even state, you have to do this. Here, sum over U mu R, this is even for A and odd for A dot. Because we have taken the A to represent the GSO even states. Okay, we have declared that this is the allowed state. A is a spinner that is allowed. So A dot is not allowed. Okay. But if you apply odd number of fermionic oscillators on A dot, okay, then it becomes GSO even again. Okay. So that's why here you can use A dot, but then this has to be odd, right? So which means that you cannot take all the U mu's to be 0 in this case. Is this clear?
A and A dot are standards for what we are calling plus, minus, plus.
Yeah, A, say even number of classes, right? Or odd number of classes, depends on how you choose it. And A dot is odd number of classes. Because you represent this spinor representation as 5 elements with plus or minus, right? Each has plus or minus. Okay, depending on whether it's using the upper state or the lower state. Okay. So A and A dot differ by how many classes you have. Well, that convention you can fix, but you just think in terms of abstractly as the S and S prime, right? There are two inequivalent spinor representations because that convention is not SO10 covariant, SO9, 1 covariant, right? It requires the choice of basis to specify the plus and minus. Whether the number of classes, even or not, that is of course invariant under the SO D,
Which one we declare as GSO even?
Exactly, yeah. So we have declared here that these kinds of spinors, okay, is GSO even. Say all plus is allowed. Let's suppose that all plus is allowed, that is GSO even. Okay, if you want to fix that convention, A corresponds to where all pluses is possibility, right? So the number of pluses is odd.
The ground state is chosen to be GSO odd because of, that was not a convention, right? That was.
Yeah, that was not a convention. Yeah, that will we'll see the origin of that when you work with hosts. Right now, it's just a specification that we put the ground state to be GSO odd. Okay, as I said, there is a hidden ghost in the ground state. Right? Just like in the bosonic string theory, there is a hidden C1 on the vacuum, right? That was there. We didn't see it in the old covariant formulation, right? Only in the BRST formulation we saw it. So here also, once you go to BRST formulation, we will see that there is a hidden ghost, and that carries odd GSO projection. Okay, that's the reason why you have this strange rule. Oh, there are two sectors. R vacuum corresponds to putting periodic boundary condition on the axis and anti-periodic on the fermions, right? So every oscillator acts on every vacuum. On every vacuum, you have to create the states by the whole list of operators, right? Just like on the NS vacuum, right? we're applying the boson harmonic oscillators. Right? You could have asked the same thing, right? So here, R or NS depends on what kind of boundary condition you put on the fermions. But after you have done that, right, then you have to find all possible states that satisfy that boundary condition, right? Which allows us to act with fermion oscillators. Right? So this NS and R, right, refer to space-time fermions and bosons, right? And that in fact came as a consequence, right? That came as a consequence of the fact that these carry spinor representation. Okay? And hence we can anticipate that these should represent space-time fermions. Right? But these are nothing to do with the worldsheet fermions a priori, right? Is that point clear? Right? So on the worldsheet, we are just constructing states, okay, which can be twisted or not twisted, right? Because we have we gave the reason for GSO projection, right? That in the x psi plus psi minus space, we do an identification. X psi plus psi minus is equivalent to x psi plus minus psi minus, and similarly x minus psi plus psi minus, right? These allows us to construct extra twisted states where the ends of the string, one end lies on x psi plus psi minus, other end lies on x minus psi plus psi minus. Okay. That's a twisted string. But every oscillator can act on that state. Right? We are not freezing the dynamics of the psi mu plus minus. It's just that you have twisted boundary condition on psi mu plus minus. In this case, yeah, that is the same as before. I have only specified the ones which are not the same. Oh, maybe not, it's not the same. Mu r, let me, yeah, this is the same as this. Okay? It should be odd. So these conditions factor between left and right. Right? Separately, we can state these conditions on left and right.
For holomorphic string. Because when you do RNS,
We'll write a dot. I mean,
then RR, you write two ways.
yeah, you have to write two A's. Yeah, A and B. See, you follow the convention, as I said once and for all, left is left, right is right. So when I write AB, right? When I write AB, A refers to left sector, B refers to right sector. Right? Then there will be no confusion. You just follow one convention. Yeah, I'll write the same way. That's okay.
How is it?
Because yeah, okay, you can, if you want, you can put a level here. Rn, this is NSR, right? Because if it's spinor, it's the same spinor, right? You don't want to use a different label. A 16-dimensional spinor S, right? It's the same S, same A that labels 16-dimensional spinor representation. In this case, the Tino, this is R. Tilde is the left, right? Remember, tilde is the anti-holomorphic is left.
Actually, last class you used tilde, right?
No, did I? No. Yeah. Meaning the conventions I fixed. Maybe I wrote things wrong, but conventions are fixed, right? That right means right movers holomorphic. Left means whatever appears on the left is left mover anti-holomorphic. Okay, so you'll fix that convention. Okay. Yeah, RNS. You have to extend basically the two levels, right? So here it will be product over n mu. And now you again have this choice A k or A prime k. No, A dot, sorry, A dot. A dot. So on these Q's and R's is the same, right? We are not going to do anything. So now the condition is that sum over U mu R. So R belongs to Z plus half now, right? This is odd because this is NS. Sum over V mu R. This is odd. What did I say there? This is even for A. Into B. And this is odd for A, even for A dot into A. So that will come later. So far I am just constructing a full Hilbert space, right? I have not imposed the Ln and Gn conditions yet, right? But before you even impose those, right, you already throw out some states from the Hilbert space because of the GSO. Is this clear? So what this is saying is that the condition on these V mu's, the what states we keep and what states we throw out, right, will follow the same pattern on in the left and right sector if you are working with 2B, right, which means that the in the lowest level states, right, when this is 0, for example, okay, if we keep the spinor representation S on the right, we also keep the spinor representation S on the left. If it's 2A, it's opposite. Now, whether you keep the spinor from the left and anti-spinor from the right or vice versa, that actually doesn't really matter. It gives equivalent theories. Okay? But whether you keep both spinors, okay, or one spinor, one anti-spinor, right, that makes a difference. Okay, that's the difference between type 2 and type 2B theories.
There is nothing called in between, right? Like phase or something which can just
Phase, meaning?
In between even and odd. Phase can be continuously.
Then you'll throw out everything, right? Yeah, then you'll throw out everything because you want invariance, right? So you better have only plus minus 1, right? So that by applying some B's, you can restore some states. Is this okay? Okay. And then RR will be this combination of the two. And now there are 4 choices, right? A, B, K, or A dot, B, K, A B dot K and A dot B dot K.
The R sectors in RMS and NS are which representations we have.
Yeah, but both are allowed. Remember here, NS, you can have this as well as this, right? But they differ by how many oscillators you are at, right? I'm not writing only the ground state, right? All the excited states also, right? So for example, if you take 2A, we have already chosen the right sector in 2A to be this one, right? A, which means you have to choose a B for the vacuum. So then in 2A, sum over U mu R is even, sum over U mu R odd for the choice AB.
Okay, by 2A simply means that it has to be the opposite, the NS and the sum has to be opposite.
Yeah, so on this side, let's fix that we will choose always A, right, as the allowed ground state, right? If you don't, that means we declare these as the even, GSO even, right? Because as I said, the other one on the right sector, right, we have a choice and both choices are equivalent, so we just fix A to be the choice. Okay? That's why, so here, for example, I have written that this is even for A and odd for A dot, right? So here, because B is, this is the same representation as that A, right? We didn't put a dot. Okay? So then, sum over U mu R should be even. Okay? And for 2A, this one, right, for the choice B, sum over V mu R should be odd. Because in 2A, the allowed ground states have opposite chirality. It's best to focus on the ground state, right? Let's look at what ground states are allowed. Okay. So in 2A, the ground states that are allowed are A dot B, right? Because you have already decided the right sector has B, right? Allowed ground state in right sector is B because, yeah, if you want port, yeah, A comma B dot. For 2A, it will be A comma B dot. That's the ground state, right? In 2B, it is A comma B. Is that clear? If you don't apply any oscillators, right? Then the allowed state in 2A are A comma B, and in 2B, sorry, in allowed states in 2B are A comma B, right? And allowed states in 2A will be A dot comma B. A comma B dot, but the right sector you already fixed is B, right? Let's just fix that convention, right? Right sector we always allow the spinor representation, right? It's the only question of in the left sector whether you allow the spinor representation or the anti-spinor representation. Okay? So it's right is always B. Okay? Left you have a choice of A or A dot. Right? It's A for 2B because both right and left should have carried the same spinor, and it's A dot for 2A. Is that clear? And then the idea that if it's not what is allowed in the ground state, right, you have to apply odd number of oscillators. Everybody looks confused. Type 2B, yeah, is this one. Okay, 2B. For AB. Right? It's just that once you understand how you assign the GSO projection to the ground states, right? Ground states are only either AB or A dot B. Right? Because you have already decided that the ground state of on the right sector you always choose to be the spinor. Okay? So the ground states are either AB or A dot B. Okay? On that ground state, okay, you you declare that that ground state is allowed in AB is allowed in 2B and A dot B is allowed in 2A. Okay. So for those, you can create excited states by applying only even number of oscillators. Okay. If you start with a ground state with opposite chirality, right, then you have to apply odd number of oscillators. Right? The rule is as simple as that.
The states with odd number of oscillators that count back in, also a complex spectrum.
Also part of the spectrum, yes, indeed.
Has this oscillator that
They cannot be.
not like a Fox space back to the oscillators of the actual back to
Because of, in this case, the reason it's not a usual Fock space is because the ground state is degenerate. Right? Ground state itself has this degeneracy, and hence you start with the degenerate ground state and you apply these oscillators, right? And then because of this GSO projection, you have this additional complications. If there's no GSO projection, right, you just start with both ground state S and S prime, both will be allowed, and then you apply arbitrary number of oscillators, right? It's a GSO projection which is cutting down part of the states.
There's nothing which takes you from type A to type B ground state. I mean,
No, type A and type B ground states are different.
Considering this A, B, K vacuum, that would be for type 2B.
Yes.
Then A, B, K, we see the GSO projection, GSO parity of that. If it is even, then we keep that in the spectrum. If it is odd, we add odd number of oscillators to make it even.
Yes.
Take that into
Exactly. Right. In type 2B, by definition, AB is allowed, even, right? So then, if you start with AB, you have to apply even number of oscillators of both kinds. Right? If you use B dot, right? Odd number of B's. Odd number, you have to use odd number of B's, but still even number of B tildes. Okay, whichever right sector you are changing or the parity of the ground state, so you have to use odd number of right oscillators.
This is even for A and also for A.
Even for? Yeah, but this is, we are assigning this to this one, right? But yeah, but you can use it. I mean, what you can do is that you can take one particular ground state, all plus, okay? Declare that to be positive. Okay? And then you apply the same UU rules also to the zero oscillators, right? So then starting from all plus, right, if you apply even number of B zeros, you get to even number of odd number of pluses. This we can check, right? Whereas if you apply odd number of B mu's, you go to even number of pluses. Yes, that's what. For no. For A comma B, right? This should be odd. Sorry, for A comma B, yeah, because you have to use the even number of B's, right? A is an allowed ground state into A, but B is not, right? So that's why you have to use odd number of B tildes, right?
Is B the right level or the left?
A comma B means B is the right level.
And then holomorphic sector is problematic, right?
Holomorphic sector is B.
So you should have
Holomorphic sector, no, holomorphic sector is not problematic. Holomorphic sector is the right sector, right? That is always assigned the spinor representation, right? That's the convention I'm taking. That in the holomorphic sector, right, the ground state always carries spinor representation, so we use a label A.
That's why U is not changing. Some of U is not changing.
Yeah, some of U is not changing. Yeah, so the rule for sum of U is the same all through, right? The rule for sum over V changes between 2A and 2. It's opposite. Rules are simple, it may look confusing, but I think once I mean, you understand, you just write any state, you will be able to figure out whether it's allowed or not allowed. Right? Just count the total GSO parity of all the oscillators and the ground state. Any other question? Okay, so now we have to introduce the physical state conditions. And as we discussed, we have to impose a T alpha beta equal to 0 condition. Why? No, there is. I didn't write everything. For A dot B dot. A dot B dot is what you want. Okay. So A dot B dot, it depends on whether you want 2A or 2B, right? So let's do 2A first. B dot is the right factor, right? It has wrong parity, right? Because the ground state should have A. Right? So this means that sum over U mu R should be odd. Right? Sum over V mu R, what is it? Even or odd? In 2A, we are doing it 2A.
Even.
This is even. Because in 2A, right, this dot is the correct ground state. Right? So you have to apply even number of oscillators. Right? If you use 2B, right, sum over U mu R has to be odd. Right? Because the correct ground state is A, not A dot. And sum over V mu R also has to be odd. Because again, sum over the ground state is not allowed, right? The B dot is not a correct ground state. Is this clear? Right? So you have to do this rule for all 4 sectors: AB, A dot, B dot, A dot B, and A B dot. Right? On each of these sectors, right, you have to find a rule of what kind of oscillators you can act so that you get a GSO even state. Okay, so physical state constants, T alpha beta equal to 0, you have seen in bosonic string theory. This comes from the equation of motion for the metric, 2-dimensional metric. Okay. But you also have to impose J alpha plus minus equal to 0. Okay. These are the supersymmetric currents. Okay. Because when you vary the 2-dimensional gravitational field, okay, its equation of motion will give G alpha plus minus equal to 0. Right? In a sense, one way to define this G alpha plus minus is that you vary the 2-dimensional action with respect to the gravitational field, and then you go to the gauge that you have fixed where the gravitational fields have been set to 0. Now, if you recall that for T alpha beta, there is one condition, one combination that you didn't have to check, and that is TZZ bar or TUV. TUV was automatically 0. Okay, because this is a trace of the energy momentum tensor, right? And for a conformal field theory, it is automatically 0, nothing to check. So you only have to check TUU, UU, and TVV. Okay. And then the conservation law tells us that del V of TUU is equal to 0, because the full conservation law would have been del V of TUU plus del U of TVU, but TVU is 0, so del V of TUU is equal to 0, and del U of TVV equal to 0. Okay, and then the expansion coefficients of TUU and TVV we call the Lenz and Lenz leaders. Something very similar happens here. What one can show is that for the x mu psi mu system that you have taken, Okay, but this is generally also true for more general superconformal theories, that Ju plus is 0 and Jv minus is 0. These are linear exercise. Okay, if you take the expressions for J mu plus minus, I remind you that we wrote G alpha as a two component spinor, right? G alpha plus and G alpha minus. And we gave the expressions for this G alpha plus, the two components of G alpha in terms of x and psi. So maybe I can write it down if I have, yeah. Okay, so G alpha was proportional to rho beta, rho alpha. These are the two-dimensional gamma matrices. Psi mu, del beta x nu, beta mu nu.
Zero, that was, you're saying identically zero, right? I mean,
Identically 0, yeah. And basically what happens is that if you consider J u, right, you will have a rho u, right? And rho u is basically rho 0 minus rho 1, right? If you look at the rho 0 minus rho 1 combination, you will find that the appropriate component is identically 0. Then it becomes a matrix whose 3 elements are 0 and 1 element is non-zero. That basically forces one of the components to be automatically 0. Okay, so these also have a consequence, which is that del V of, okay, del U of Ju minus plus del V of Jv minus is 0. This is the conservation law, right? Current is conserved. But Jv minus is 0, so this is 0. Right? So del U of Ju minus and similarly del V of Jv plus is 0. Okay? So this means that Jv plus is a function of U only. This is, of course, once you satisfy equation of motion, because these conservation laws are valid only after you have satisfied equation of motion. So Jv plus is a function of U and Ju minus is a function of V. Okay? This is just like TU become a function of U and TVV become a function of V. Right? And those, after you went to the Euclidean space, these become the holomorphic and anti-holomorphic operators. Right? Similarly, here, this will become a holomorphic operator and this will become an anti-holomorphic operator.
The traceless is from the systems that comes from Y.
From Y, yeah.
So this follows from
Super file, basically, yeah, exactly. Okay, but for this xi system, you can explicitly check. Just like the tracelessness of the xi system, you can check explicitly, right? You construct the energy momentum tensor and take the trace. The same is true here.
Because T is 0, we are getting that holomorphic condition there, and this is the analog of that.
Yeah, this is the analog of that. Okay? Because the J has some component 0, you are getting the holomorphicity of these currents. So now we are going to implement these constraints that we had found in the same way as we implemented the constraints for the T. Namely, we don't demand that as an operator, this is 0, okay, but that its matrix element between two physical states should be 0. Okay. So you expand in modes, and then you require that the positive modes will annihilate the physical state. Right? That's the same principle you will follow here. Is clear?
One sector, this also has a zero mode like that.
Yes, in Raman sector, this will also have a zero mode. And there will be, because G's are also, the moding of G is correlated to the moding of the psi, right? X is always integer moded, right? But psi is integer or half integer depending on whether Nebel source and Ramon. And the G will basically follow the same. So we expand JV plus as sum over R, GR e to the I R sigma, and JU minus sum over R, let's call it R prime. Okay, these are a priori functions of tau, just like what we did for the energy momentum tensor. And then we demand that ln acting on physical state. Okay, let me write this. Okay, I'm going to put the subscript m from now because m stands for matter, right? Which is the L coming from x and psi. This is a full L for now, right? But I'm putting this superscript because later on we'll also have the ghosts, right? Which will contribute their own L's. So m stands for matter. Both are, sorry, G, tilde. Matter, which means x and psi. So we'll demand that lmn plus c delta n0 acting on physical equal to 0. Oh, here I should have said that R belongs to Z plus half, R prime belongs to Z plus half in NSNS. R belongs to Z, R prime belongs to Z plus half in NSR. R belongs to Z plus half. Okay, this just follows directly from, it follows in many different ways. You can either write the expressions for psi del x that I have written, J mu, right? And if psi is antiperiodic, J is antiperiodic, and if psi is periodic, J is periodic. Right? It follows from there. Or it follows from the fact that when you do a Ramon sector or an NS sector where x and psi have opposite boundary condition, right? X is periodic, psi is antiperiodic, then the corresponding epsilon also has to be antiperiodic. Okay, and if epsilon is antiperiodic, its corresponding Noether current will also have to be antiperiodic, right? It also follows from there, these mode expansions. C is a normal ordering constant. Let me write the other one, then n plus C tilde delta n0 acting on physical equal to 0. And then we'll also demand this for n greater than or equal to 0. And then similarly, GR acting on physical equal to 0, G tilde R acting on physical 0 for R greater than or equal to 0. Yes, indeed. C and C tilde will be the analog of that -1 in the bosonic case. Right? This is so L0 I'm taking to be normal order. Right? Any constant that appears is part of C. So these are normal ordered. For G's, you don't have to worry, right? Because G has a cross term between psi and x, right? Okay. So there's no ordering ambiguity there, because the psi oscillators commute with the x oscillators. Okay, so for G there is no issue of normal ordering.
There's something about the modeling of series follows from epsilon and epsilon.
Okay, yeah. Yeah, so the first of all, the modeling of G follows also from the psi and x. That if psi and x have opposite boundary conditions, G will be antiperiodic, right? So that means that in the GSO, in the NS sector it will be modeled half, in the Ramond sector it will be modeled by integer, right? But the other way to see this is, imagine that you are in the NS sector. Okay? So in the NS sector, psi and x are related by supersymmetric transformation, but the epsilon has to be antiperiodic, right? If epsilon is antiperiodic, its corresponding Noether current, see J is the Noether current for epsilon, right? That should also be antiperiodic, right? And that will mean that G will have to have this half integer modeling. No, because G0 involves the product of psi and x, right? There's no ordering there because they commute, right? So G0 has no problem, right? It's the L0 which has problem. So I'm going to write down the expressions for L's and G's. And for G's also I should put M. Okay, because in the full theory, there will be contribution from the coasts. Right? Both G and L will get contribution from the coasts. Okay. So let me write the expressions LMM. This M is just matter, right? So this M is not an index. This part you will recognize is the same as in bosonic string theory, right? Because after all, I mean, we have not changed the bosonic part of the action, right? It's the same action, so it's the same. This is the extra term that comes from the fermionic contribution to the T alpha beta. So LM tilde has similar with alpha replaced by alpha tilde and B replaced by B tilde. And notice that this expression is valid in both Ramond and Nebel-Schwarz sector, even though this index R takes values over different, that takes different values in the Ramond and Nebel-Schwarz. Okay. In the Nebel-Schwarz sector, this will be half integer. In the Ramond sector, this will be integer. Okay. But the same expression remains valid. Is it clear? Any question?
L0 you have to write.
L0 I have to write, LM0. This is for m not equal to 0. And similarly for LM tilde, L0 tilde. There are questions? Okay. So I'll also give the G and G tilde is similar. Okay. So the idea is that with these expressions now we can take those, apply it on the physical state, and start constructing the spectrum. I'm going to use this, impose this physical state condition.
I can take either half integer or integers depending on whichever you are.
Yes.
But n, the sum over n also changes over that?
No, n, because n refers to alpha index, right? N is always integer. Okay. So the index, I have not written what they are running over, right? But it should be clear from where they appear, right? So n is always an integer because they are an index of alpha. Any question? Now to construct the spectrum, we need one missing information, and that is the value of C. Without knowing C and C tilde, right, we cannot construct the spectrum. And again, here I am just going to give you the result for C and C tilde. Right? It comes by again demanding the absence of negative norm states, just like as in bosonic string theory. And as you saw in the case of bosonic string theory, that if we just look at the phi theory, right, then we can put constraints on C and C tilde, but you cannot completely fix it. Right? Fixing C and C tilde and D requires going to the interacting theory. We will avoid this and we will directly get these conditions from Beer-Stein invariants, right? From demanding that the QB squares to 0. Okay? But for now, we will just give the values of C and C tilde and proceed to construct the spectrum from there. Of? Exactly, yeah.
That we can do here also.
That we can do here also. That is the same principle.
gave some argument about sigma going to minus sigma to set C equal to C tilde. That we can get.
Yeah, that, okay, if in type 2A, in type 2B we can, sorry, in type 2A we have a, sorry, type 2B you have a symmetry under sigma goes to minus sigma because left and right are the same, right? So you can do that there. In 2A we don't have that argument, okay? But we can individually fix C and C tilde. We don't have to assume that, right? In the absence of negative term states, we'll fix both C and C tilde. So C, so we have result without proof for now. As I said, that I mean we can again prove it in different ways. We can also work in the light cone gauge, for example, to fix this, right? Demand that the algebra closes, okay? But we will be just focusing on the BRST formalism because we have, that is needed to construct the interactions anyway. Okay, and there everything will follow from Q square equal to 0 condition. Okay, so the result is that D is 10 first of all, okay? And C is minus half in NS and 0 in Ramon, and C tilde is the same. C tilde is minus half in NS and 0 in Ramon. Okay, and it doesn't care whether it's 2A or 2. It's the same result in 2A and 2B. Is this clear? So we will first work out the mass shell condition. Okay? And if you recall, in the bosonic string theory, the mass shell condition, right, what masses are allowed, came from applying L0. Right? So we'll see what L0 constraint tells us in this case. So let's take a state like this. So NS. So L0M plus C acting on, so let's call this state S. We need to demand that this is 0. Right? And then from the structure of L0, here, we basically see that for every alpha oscillator you pick up N, and for every B oscillator you pick up R. Right? Because alphas are really normalized as square root of R times creation operator. So this translates to sum over N. Sorry, plus, I forgot the L0M also has this contribution, right? This momentum dependent contribution. This one. Similarly, the L0 tilde gives you to sum over n. So m square, which by definition is minus k square, will be given by 4 over alpha prime times this whole thing. But it's also equal to 4 over alpha prime C and C tilde also in the bracket. Thank you. So these are known as the levels. Okay, similarly, this also called a level. So besides giving the m square, right, this condition also tells us that the levels has to match. Right? This is the generalization of the level matching condition that we had for bosonic string theory. And C is minus half, C tilde is minus half. So let's try to consider the lowest mass square state for NSNS. Yeah, we are doing NSNS only here. Right? This whole thing is for NSNS. So what is the lowest mass square state?
GSO.
No, including GSO. Yeah, so what is the state? Because of the GSO, right, the lowest would have been when this level is 0, right? But level 0 is not allowed because you have to apply at least a b mu minus half, right? Okay. So lowest state is that you put that r equal to half, right? And here r prime equal to half. Okay, and these two set equal to 0. Okay. So lowest mass square is zeta mu nu b mu minus half b tilde nu minus half acting on k. This has k square equal to 0. Okay, because C is minus half and this is half. So these will give the graviton-dilaton antisymmetric tensor field of type 2 string theory. Is this clear? Yeah, because this will give the graviton-dilaton antisymmetric tensor, right? It has exactly the same degrees of freedom. Zeta mu nu, right, is can have symmetric part, antisymmetric part, and the trace part, right?
That totally comes from alpha minus 1 alpha.
No, alpha mu minus 1, alpha tilde nu minus 1, right? Acting on the vacuum is yes or odd.
No, I thought he's referring to bosonic string.
Yeah, in the bosonic string theory we had, right? But we are not combining bosonic and superstring, right? This is in superstring theory, that state is not there. Because that state will be yes or odd, right? Okay. That state is not there. Right? Instead, this state is there, okay? And the tachyon is not there. Yeah. So the ground state would have been tachyonic, but the ground state is projected out because it's yes odd. Is it clear? Okay. So the massless spectrum from the NSNS sector is the same as the massless spectrum in the bosonic string theory. Okay, except the D is 10 instead of 26. The other constant basically comes from the GR half on the state equal to 0, right? L1 is a GM. Okay, LN1 will not do anything because that will lower the index too much. So basically it comes from these. So I'll leave it as an exercise to check that this gives you this K mu, zeta mu nu, K mu, zeta mu nu equal to 0, and K nu, zeta mu nu equal to 0.
Here we have the same results, right? The high enough present, high enough
Yeah,
present.
because that's why L1 I didn't use, because L1 will already reduce it too much, right? It will reduce it to a positive index, and that annihilates the vacuum anyway, right? So in this case, these are the only two conditions you have to check. Okay, and you can more or less see, I think, from here, right? That Gm, if you take R equal to half, right? The term that contributes is from here. B mu half P mu, right? P mu will generate a K mu, right? And B mu half, right, will act on, will have a non-zero anti-commutator with this, right? Given eta mu nu, and that gives you this basically K mu zeta mu nu equal to 0. Okay, and similarly, this G tilde will contract to the second index, K nu zeta mu nu equal to 0. Is this clear? Let's do the Ramon sector.
Right now, till now, we have talked about the mass stress part of the.
Yes.
Because we are working superstring, should we say about the spins of this states also?
These states? Yeah, so this is the same spin as for graviton-dilaton antisymmetric tensor field, right? It forms a symmetric tensor representation, antisymmetric tensor, and a traceless scalar.
But the new thing will arise when we go to the new.
Yeah, exactly. So let's focus on the bosonic states, right? The only other source of bosonic states is the Ramon-Ramon, right? Because RNS and NSR are fermionic states, right? Because they carry spinor representation on the one side and vector-like representation on the other side, right? So those will not give bosonic state. So let's look at the Ramon-Ramon sector and see what we get. So I'm not going to write down do this whole thing again, but the mass cell condition This is basically coming from L M0 L tilde M0 is the same with C equal to 0 and C tilde equal to 0. When I say the same, basically I mean that the structure remains the same, even though the values over which R runs, of course, changes. Right? In the Ramon sector, R will be over integers instead of half integers. But this structure remains the same and C is 0. So then the massless states are A, B, in 2B and A dot BK in 2M. Right? So the massless state means you have to basically focus on the ground state. You can't apply oscillators. Right? Applying oscillators will raise the mass square. So this gives you product of two spinors, and this gives you a product of spinor and anti-spinor. Okay? And this now you have to figure out. So these are both tensors, right? Because spinor times spinor gives a tensor, spinor times anti-spinor gives you tensor. Right? So you have to figure out what kind of states it describes, and then what kind of fields correspond to those states. Right? So what one finds is that this one corresponds to a scalar 2 form C mu nu, and a 4 form, let me call this C2 mu nu. But this 4 form has a peculiar property that DC4 is the same as the Hodge dual of DC4. Okay, Hodge dual, it's flat, Hodge dual in flat spacetime. So you take a 10-dimensional epsilon symbol, right? And this has 5 index. Right? Contract the 10-dimensional epsilon times 5 of the indices with the derivative of C4, and what you get is the same as the original one. Right? That's the meaning of the self-duality condition. Okay. Now this looks a little strange, right? The way it comes, see, the way we get the spectrum, right, is that this analysis only gives a state and in which representation they belong to. Right? Starting with that information, what states are there and which representation they belong to, you have to ask what kind of field theory will produce that states after quantization. Right? So there is a step involved in saying that these are the fields which are there in the theory, because you don't get fields directly. Okay? What you get from the analysis of the spectrum are what states you will get if we had quantized that field. Okay? Just like for G mu nu, right? We don't directly see the G mu nu. What we see is that if we had quantized the metric, right, you know that you get certain kind of states, right, labeled by 2 index with some constraints, and that's what you then use to work backwards and say that if you had a metric and if you had quantized it, you would have gotten those states. Cleb's Gordon will tell you the representation theory and what kind of particles you get, right? Because these are leveling the states, not the fields.
Like for instance, in 4 dimensions, when we have half comma 0 and half comma 0, it's like that only, right? 2 chiral objects.
Yes.
Trying to build up.
Exactly.
So half comma 0 and half comma 0 will give you a scalar and a what else you call it? 1 comma 0. No, not vector. 1 comma 0.
B mu nu.
No. 1 comma 0 is
B mu nu. Yeah. That's the confusion. That you know the what representation it gives, right? But then you have to figure out what field actually gives that state.
The degree of freedom matching you can do.
Degree of freedom matching you can do, yeah. Right?
Non-unique.
But degree of freedom of type 2 and type 2, we have the same degrees of freedom at the end. Because you can see it's like this product, no?
Yeah, but chiral and anti-chiral.
Yeah, it will go. It will go in, right? So because you know what states in which representation they are transforming, right?
But since if I had half comma 0, different from half comma 0, 0 comma half.
Exactly.
So just give me half comma.
Yeah, half comma 0, 0 comma half is a vector representation, right? Half of is vector representation.
Yeah.
But half comma 0 times half comma 0, right? At 1 0,
Plus,
yeah, it's a scalar plus antisymmetric tensor field. Yeah, B mu, you know.
it's not easy.
Yeah, so you first read out the spectrum from here, then you ask what field theory will produce this spectrum.
And that's the leap you have given.
That's
That's the gap you are saying is here, like, you know, the scalar.
exactly, yeah. I mean, if you had written down the field theory from the beginning, right, and that's what string field theory does, you can write down the kinetic term of string field theory directly. There you know what fields are there. Okay, but here we are just constructing the spectrum. So from the spectrum, you have to do some work to read out what field theory would have produced that spectrum.
Weak answer to this in a generic.
Yeah, it's simple enough so that there is a unique answer. I mean, if you give the representation of the particle, right, you are not even talking about interactions or anything, right? You are asking what free field theory will give. Yeah, that's what free field theory will give that particle. That is a unique answer.
Bosonic case would be Bosonic case is just for the
Yeah, well, we did this indirectly because we got a zeta mu nu, right, satisfying k mu zeta mu nu equal to 0, right? And then you have to ask what quantum field theory will produce that kind of particle spectrum, right? And that quantum field theory was the theory of metric plus antisymmetric tensor field plus scalar. See, if you had just taken the zeta mu nu, right, rank 2 field, you decompose into symmetric and antisymmetric part, and you would have concluded that you have only metric and antisymmetric tensor field, right? The scalar you would have missed, right? You got the scalar by looking at the physical spectrum, and then you notice that if you had started with the theory of the metric, even though H is not traceless, when you quantize it, right, you only get 2 polarizations, not 3. Right? Or that is in 4 dimensions. In D dimensions, there is an appropriate counting. So you really got the underlying field theory by comparing the spectrum.
I mean, from the spectrum, the particle spectrum, we can actually, I mean, take the other side field theory and just calculate this, quantize it and match the spectrum. That's one way we are doing over here.
Exactly.
But what you can do it at the level of field theory also, you're saying.
Yeah, but for that you have to write down the string field theory for this theory. Right? We are not doing that. We are just constructing a spectrum at this stage.
This we call as a self-dual.
Yeah, this is what we call the self-dual 4 form. Right? Self-dual 4 form basically means that its field strength, which is the 5 form, that is self-dual. Okay. And then for 2A, the spectrum is a vector C1 mu and a 3 form. Here there is a condition on the field strength.
But we have match with the fields on the other side.
Hmm.
We can only match the kind of fields we have. We can't match the interaction between us. Right?
Yeah, so this is, we are not writing on the interaction at all here, right? Interactions, for that interaction, to get the interactions, you have to calculate the scattering amplitude, and then you ask what kind of field theory you would have to produce that scattering amplitude.
what are the physical state conditions here?
For this case, all the physical states conditions are automatically met, right? Because it satisfies L0 equal to 0 condition, because C is 0, right? We are not applying any oscillators. So if you look at that, right, this C will be replaced by 0, right? No oscillator is being applied, so M square is 0, and anything with positive index, right, will automatically kill it, right? Because you are in the vacuum. So all states are physical in this case.
The number of states is a 16 square, right?
16 square, yes, exactly. 16 times 16, yeah, A and B each run over 16 Oh, here. Oh, here to count it, you have to first take each form field, quantize it, see what kind of spectrum it will give, and then you can count. Well, you can. I mean, yeah, you probably can, right? If you take 10 dimensions, then this will give you how many? T minus 2, right? So that is 8. And this is a bit complicated. You have to figure out how many it gives. Yeah. It can be done, yeah. Yeah, okay. Yeah, so you can do this. Okay, now let me just say a few words about the RNS and NSR, but there's nothing much to say really. So let's do NSR. So here R means that on the right sector you have Ramon, right? So in this case, the massless states are B tilde mu minus half acting on A. Okay, left sector is Neveu-Schwarz. So you have to apply what you did on the left sector here, right? So you basically pick for the left part what you did here, and for the right part what you did there. You can multiply by zeta mu. Okay. And the physical state condition, the G half acting on the state, sorry, G tilde half acting on the state gives you K dot zeta equal to 0. We call it zeta tilde mu. And RNS is exactly opposite. This is A or 2B or A dot or 2A. RNS, let me write it. And K, of course, is always there. I didn't write. And you have again K mu, zeta mu equal to 0. Sorry, zeta mu, yeah, this is important, A. And this is A or A dot. Or A dot. Is this clear? Yeah, you are just combining what I did in the NSNS and what I did in RR. Right? Half of one, half of the other. So you can probably guess where these things are going to come from. These states. State which carries a mu index, one vector index, one spinor index. These are the gravity node, right? This is what we call spin 3/2 in 4 dimensions. 3/2 is specifically in 4 dimensions, right? In 10 dimension, it is a radiator Schwinger field. Right? It's not you can't call you don't use SE2 levels, right? Yeah, so that's also not true. Meaning it's a rank 2 tensor, but not spin 2. Okay, so these are the gravity nodes. And we see the difference between 2A and 2B. Right? You have 2 gravity nodes, right, in both theories, because you get one from NSR, one from RNS. Okay? But in 2B, both gravity nodes have the same chirality, right? Because both carry this index A. In 2A, this one always carries index A. but this one can carry index A dot. Right? So in 2A, the two gravitons have opposite chirality. In 2B, both gravitons have the same chirality. And it so happens that I mean, independently of all this, right, you can construct supergravity theories in 10 dimensions. There are two supergravity theories with maximal supersymmetry, type 2 and type 2b, and their low energy spectrum is exactly this. See, here you don't see any supersymmetry in space time, right? From whatever I have done, the bosons and fermions come from very different sources, right? The bosons come from the NS-NS sector, fermions come from NSR or RNS sector, right? And bosons come from NS-NS and RR. Nevertheless, the fact that it comes from low energy theory of that its spectrum agrees with the low energy spectrum of supergravity theories suggests that this has supersymmetry. Actually, the spectrum certainly has supersymmetry, but this is an indication that the interacting theory is also supersymmetric. Okay, that of course I have not proven because I have not even introduced interactions. Right? We will see later how to try to prove this.
The number of fields and the type of fields that with respect to
Exactly. That's right. That's right. Yeah.
Dilating was also absorbed. What happened?
Dilating. Yeah, I think these I mean xi mu zeta mu a, right? Just like there zeta mu nu contain a scalar, here also this will contain a dilatinum. Right? So this has spin 3/2 and a spin half, right? Because basically the spin 3/2 also has this extra constant, I think. Pardon? Okay, not yeah, what about Radhika swing? Right? It has a Radhika, it has two independent representations hidden in it. Okay, so I think I'll stop here and we'll continue next time. And we'll see what we continue next. Okay, this Thursday there will be no class. From next week, next week is regular, right? There's no that conference is not starting next week. Conference starts the week after. Okay, next week there will be regular classes. That week after I have to reschedule the talk, the classes in the afternoon. That we'll see. But, what? Yeah, next week I think there's a confusion, right? Next week there's a conference.
I think this is not part of the class. In the talk, you made a comment that we don't quite know the action for type 2 visit. But low energy
Yes.
action, something like that.
Yeah, you can't write an action for time. You cannot write an action
For type 2.
for type 2 from which this one follows. No. Self-dual fields, right, don't have an action. You have to put that as a constant.
Cannot just write these square.
What?
1 over 4 1 over.
Yeah, if you do f square, right, the fact that it's f is a self-dual field, that is not put in, right? It will have both the self-dual part and anti-self-dual part.
Are you saying action will not tell you?
Action will not tell you that you have to project it.
like a constraint system, right? You can,
But a constant, in this case, a constant is not algebraic. If you have an algebraic constant, it's okay, right? Phi square, phi 1 square plus phi 2 square equal to a square, say, right? That's an algebraic constant. In principle, you can just eliminate phi. Here, the constant is on the derivative of the field, right? Because d C4 is self-dual, right? So that's the reason we cannot write. We cannot just impose this as a constant explicitly.
Right of the action.
Yeah.
That quantize it. And
Yeah.
then the quantized thing, I can remove some of the.
Yeah, except that then you can do it. Except that then you have to make sure that in all interactions those things decouple. That what you are removing, right?
But the first.
Suppose you want to write an interacting theory, right? In interacting theory, you have to make sure that the interactions are such that all those things are removed.
you can't, let's say you can't write down the action because you can't impose the constraint on the field, right?
Hmm.
But you can write down the equation of motion and impose the constraint on that, right? Because
Yeah,
equation of motion are only in the F's.
Exactly. Yeah.
Equation of motion are fine, right?
Exactly. Yeah. Equations of motion are fine. There's no problem with equations of motion.
You just now said, right? The spectrum and all agrees with supergravity.
Yes.
And supergravity actions we know it.
Type 2B supergravity has no action.
But it has a supergravity.
Yeah, it is supersymmetric, but it has no action.
Where has
Type 2 has.
And the problem is in the cell dual
Yeah.
aspect, how to impose that at the level of action.
Exactly. Yeah.
But the fermionic part has no problem. We can write down just fermionic terms. There's no
Yeah,
constraint
yeah.
there.
Fermionic term there is a problem.
But this is a very general problem, right? As you said, this is the constraint on field strengths, not on the fields.
Yeah.
So you can't do anything.
Yeah. I mean, there is a way to, I mean, there are ways to do it, but not standard ways, right? You can double the number of degrees of freedom and then half the degrees automatically decouple, right?
Something which they do in dissipative systems.
Similar to that, yeah. Right? But
All dimensions. Not specific to
well, self-dual fields exist, I think, in 4p plus 2 dimensions, where p is an integer, right? So 2, 6, 10, you can define self-dual fields. Yeah, just like chiral scalar in 2 dimensions, right? You can write action for chiral scalar in 2 dimensions. So when I said that it agrees with type 2 supergravity, agrees with the spectrum, because in type 2 supergravity also one writes the equation of motion, but not the action.